And thank you.
Thanks, Greg, for the introduction. So I'm Prasun, as you mentioned. I'm a postdoc at JILA. So as far as I know from the audience, that you guys are probably not don't work on accretion. So please stop me whenever you wish. I'm free to answer any question in between the talk. Okay. So this is basically an accretion flow. This is a black hole and a matter surrounding it, foiling the black hole, and energetic events are happening. So I am going to talk about how magnetic field is being generated in this kind of accretion flow in situ. So you have a seed field and how it can grow and keep amplified. Yeah. So yeah. So from the title slide, I borrowed it, I think, from Iranian author, 1,000 splendid sun. I just changed it to simultaneous sun. So this is an AGN, which is like billion or more than that times brighter than the sun, which generally is like residing at the galactic center. This is a famous X-ray binary where a black hole and a companion is there, and you can see jets are going out, energetic flows are going out from the central region, central engine. It's also, I think, much more brighter than sun. And this is something called protoplanetary disk, which is a matter distribution around a young star. So, what is the source of this energetic sources? Something process called accretion, which is much more efficient even than the nuclear fusion. For example, I think efficiency of nuclear fusion is around 0.7% or so, while it is around 10%. It can go to more than 100% in case of spinning black holes. Yeah. So the word accretion refers to the accumulation of matter around a centrally gravitating object. Now, when the matter is spiraling down to the central object, it loses its gravitational energy and is being converted into the thermal energy, and you get such a huge luminosity. For example, this is a black hole. It is cartoon diagram, obviously. It's not a real image. And a companion star is there, and it's just brightening down, spiraling down. And this is like jets. And this is for an AGN where there isn't a companion, but it has a surrounding medium which is quite dense, and it's just filling out in the central black hole. Now, broadly speaking, depending on accretion disk geometry, physics, we can classify the accretion disk in two categories: a geometrically thin disk and a geometrically thick disk. So I'm mostly focusing on the disk around the black holes. So please don't bother about the disk around the young stars. So geometrically thin, when I say geometrically thin, when H over R is much less than 1. What is H? H is the thermal scale height, and R is the cylindrical distance from the black hole to the point where you're measuring the scale height. So if H over R is much less than 1, what is happening there? Basically, the accretion is happening in quite a moderate rate. So it is dense enough so that cooling is efficient, and the medium is optically thick. So whatever heat is being generated due to the process of accretion is being radiated away instantaneously. So this becomes cool and it remains thin. So this is a simulation from Matthew discussed one of the work where you can see the disk and a halo like here. We call it a corona, and black hole is sitting here. But on the other hand, there can be geometrically thick disk, and it can happen in two different extreme regions. For example, if your accretion rate is too low, then there is not too much of density, and the medium is optically thin. So whatever heat is being generated, it is basically it doesn't interact. It just escapes, and the medium remains hot, and it pops up, and it becomes geometrically thick. It becomes almost quasi-spherical. So this is from one of my simulations where you can see how thick it is compared to the geometrically thin disk. And we call them radiatively inefficient accretion flow, or RIA. On the other extreme, if the accretion rate is too high, it's like super Eddington. It is so high, density is so high that even photon cannot escape. It is trapped in that flow, and it also becomes hot and popped up. And these are called, some of the models are called slim disk, put forward by Abramovich and his collaborators. So in this talk, mostly I will focus in this regime, in geometrically thin disk, but sometimes I will also refer to some of the results where I compare the difference in the magnetic field generation process between the Raya and the thin disk. Okay, any question? Because this is the important basic things, and if it is not clear, please let me know. Otherwise, things will be lost in between. So should I go forward? Okay, good. Now, in next few slides, I'll give a brief background on the physics of accretion disks, some of the important concepts. First of all, is called angular momentum transport. Now, in any kind of this kind of disk, it is thought that they are rotationally supported. That means the material is rotating so fast that the gravitational pull by the black hole is balanced by the centrifugal barrier. So, in order to fall it down, in spiraling it down, it needs to lose angular momentum. So, you need some kind of friction, right? Now, Sakura and Tsunaev in their seminal paper, 1973 seminal paper, proposed an emergent viscosity of turbulent origin called alpha viscosity. So you can see nu t is basically CS is some velocity scale, h is some length scale, and he just put some parameter in front of that it's alpha, which takes care of the all the approximation of turbulence. It's beautiful. It's simple. It's I think it's pretty good for observers, but not for physicists in that sense. So because they didn't talk about the origin of turbulence, they just told like there might be some origin of turbulence. It can be hydrodynamic, there can be global instabilities. People have proposed different kind of instabilities, but they were not successful enough to produce the observed accretion rate, which can be inferred. The first breakthrough actually came when Balbus and Hawley in 1992 proposed a weak magnetic field instability. Actually, not proposed, rediscovered, which is originally proposed by Velikiv and Chandrasekhar in 1960s or late 1950s. And nowadays we think that probably it is the instability which can explain the observation. Requirements of this instability is very simple. You need ionized medium, weak magnetic field, and radially decreasing angular velocity. And these are ubiquitous condition in XRB accretion disk around X-ray binaries, and also the inner part of the AGN disk, and also even some region of the protoplanetary disk around the young stars. So it is basically because of the unstable slow modes. But if I want to really explain it, I need to just chalk out all the dispersion relation, and I don't want to do that. I want to give you a mechanical picture of that. Think about an accretion disk around it, central accretion. Think about these two particles, blue and red. They are threaded by vertical magnetic field. It can happen for any kind of magnetic field configuration, but just for simplicity, I'm taking it to the vertical. So here, magnetic field acts like a spring, so you can stretch it. So they are in a circular orbit, and we are assuming the velocity profile to be Keplerian. So Keplerian frequency goes up to the minus 3/2. So if it is farther out, it is moving slower. If it is closer in, it is rotating faster. Now let's perturb them. Blue one inward and red one outward. So what will happen? It is rotating faster, it is rotating slower. So there will be a resulting torque on the blue one by the red one. As a result, it will impart the angular momentum, or it will transfer the angular momentum to the red one. So it loses the angular momentum, so fall inward. It gains the angular momentum, so it goes outward. And the resulting returning torque, because of this displacement, will be larger. So it's like a runaway process, and the instability grows. But what I am saying you is in the linear regime. But if you want to connect it to the observation, we need to study this instability in the nonlinear regime. So we need to do simulation. Anything? Any question? Yes.
For the geometrically case.
It's for anything. It's in like a generic instability.
Okay.
You don't have to bother about an accretion disk. You can do it in lab if it is possible. Some people are trying to do it. For example, Hantaoji in Princeton, they're trying to make experiment on that. Yeah. So that is the beauty of this instability.
We need to do an experiment.
Yes. Yes.
In terrestrial with liquid metals.
Yes. Yes. Yeah, even I think they performed already a mechanical analog in water, I guess. Okay, good. Now, so we have seen magnetic field plays an important role in determining the dynamics of accretion flows. For example, we have seen it is responsible for the angular momentum transport. And angular momentum transport becomes more efficient if we have a large scale magnetic field threading the disk. It becomes at least 100 times much more efficient. Also, it plays an important role in producing jet, the beautiful jet, not this one. Yeah, I have not seen the figure. In M87, the famous jet, which is pointing towards us. And this is the polarized image of M87, which also shows that at the jet base, there's a presence of a strong colloidal flux. So, and also different theories of jet, it supports that we need large-scale magnetic field close to the black hole in order to produce that. What were with the model like Blandford-Snag or Blandford-Payne? And also numerical simulations also have shown that it's a prerequisite to have a strong colloidal flux close to the black hole in order to produce the jet. So yes, large-scale magnetic field is important.
So is this is the conclusion that a stronger magnetic field transports more angular momentum
Yes.
faster?
Yes.
Is that just from the MRI, or is there observational?
Not observational. It's even if there is no MRI, ideally large scale magnetic field stresses can also transport angular momentum. For example, magnetic braking, because MRI generally goes for stresses, maximum stresses, which are of turbulent origin. But you can also have large scale magnetic stresses. It's like strings. But MRI becomes, in this context, I'm saying that MRI becomes more efficient in transporting the field. Yep. Okay. But what is the source of this large scale magnetic field? We don't know. I don't think we know that, but there are two plausible origins. One is the field is being generated in the disk itself by a dynamo process, where the kinetic energy is stored in the disk, like because it's rotating so fast. So huge amount of kinetic energy reservoir is there, and it is being converted into magnetic energy mediated by MRI turbulence. And actually, this is the focus of the talk. Okay. And second is that you accrete the magnetic flux from some external sources. For example, an extra binary, the companion star is like K or M type star, which shows rigorous magnetism, and they can contribute magnetic flux in the form of wind or accretion. But how to transport them is another question. It's a big question. And this is another research topic I have worked on this too. And if you're interested, you can look at papers. So in this talk, actually, basically, I will focus on this paper, which you recently put on the archive. I'm just advertising it if you want to look at it. So, yeah, with my co-authors, Avijit and Kandu. But also sometimes I will touch upon some results based on my previous results. Also, again, advertising, if you're interested, you can look at them. Yep. So now simulating the disk. As I told you that if you want to study the MRI in the nonlinear regime, we need to rely on simulations. There is no analytical theory on that. So this can be done in two ways. Either we can do just direct global simulations, and that can be done in MHD or in relativistic MHD. Some people are doing also in PIC. Yeah, so I'm not bothering, but I'm doing some plasma here, MHD plasma. Also, you can do local shearing box. So what is local shearing box? I will tell you in the next slide. But what we do basically is solve mass, momentum, and energy conservation equation along with the induction equation, which basically governs the evolution of magnetic field. And we also put a constraint that there cannot be any magnetic monopole. And we just initialize the density, pressure, velocity, magnetic field, and look at it, evolution. Yeah. So next, what is the shearing box? Because that's what we do in this work mostly. So we basically take a chunk of the disk and construct a differentially rotating box here. Here, this Cartesian box, x is analogous to the radial direction, like this. Y is like azimuthal direction, like phi, and z is the usual vertical direction. So, and shear is only in the x direction. So there is no vertical shear here. Okay. And please note that this Cartesian box, theoretically, when it is done by expanding at the lowest order of H over R. So if it is valid only for geometrically thin disk. We cannot wait for geometrically thin disk. It's not valid. Yeah. Now, something on the our simulation setup. So
I'm sorry,
Yeah.
I always have this question I never asked you. Can you go back to the previous slide?
yes, sure.
If you're at the top of this box,
Mhm.
how much gravity points down in the Z compared to radially?
Okay. So
Is it
the
essentially nothing? I mean, is
no, it's
It
significant.
is.
That's what the stratification comes.
It's H over R.
Yes.
That's the ratio.
okay, so it's just H over R.
Because
the angle.
gravity points towards the central object.
So it's
So it's just vertical
the
projection
mass of the
versus-
black hole. It's not the mass of the disk. The
No,
mass of the
no,
disk
No,
is on the
There is no
outside.
self gravity.
It
It's
is not.
yeah, no self gravity. Yes. So we have performed stratified zero net flux shearing box simulation. Stratified means we have considered the vertical gravity. So Z component of the gravity. So there will be term in the equations. We don't switch it off. And zero net flux. That means total net vertical flux is zero. So, for example, here what we use a sinusoidal variation of the Bz, net vertical flux. So, if it is downward for x less than zero, if it is outward like upward for x greater than zero. But it's not an abrupt change like a sine wave, so gradual change. Okay, so now if I just fix this condition, so over the simulation duration, there will be no change in the vertical flux. It will always be zero. Okay, that is an important thing. So our box size is, I think, 3 cross 12 cross 8, which is the optimum because we have some results from earlier works, which shows that the results actually depend on the box size. So we tried to minimize the effect of box size, and we have taken the optimal size, which is pretty good. I think. And we initialize a weak magnetic field, plasma beta of 10^4. Plasma beta is the ratio of gas pressure to magnetic pressure. So it's a pretty weak, and it gives a good environment for MRI to grow. Now let's see how it evolves. For that, I will show you how Alfvén speed, this quantity, varies over time over it in the X-Z plane. So this is the mid plane. You are at the top, looking at the bottom. Let's see. Oops.
And how is it normalized?
Sorry.
Yeah, how is it normalized?
So CS is 1. So
Okay, it's
yeah,
normalized to the speed of
Yeah.
sound.
yes.
And is it isothermal?
Yes, isothermal. Yes. Because it's a good approximation for thin disk because cooling is efficient.
I'm not sure I understand. So what's making the change in Alfvén velocity here with in the
Because
Z direction?
uh,
Density or magnetic
Density.
field?
density falls as Gaussian. We use the Gaussian profile. Rho is rho 0.
Oh, so this is a combination of density and the sinusoidal magnetic. field.
Yes.
And so gravity, just to clarify.
Yeah. Sorry.
The acceleration of gravity is proportional to height.
Yeah.
It's not constant, it's proportional to Z, and it reverses across the, so it goes like this.
Now you see the channels, the lateral motions, which is like a typical feature of MRI when it's transiting to the nonlinear phase, and now it becomes turbulent totally. So and in the turbulent region, like in the quasi-stationary state, we found the Maxwell stress when we normalize with the gas pressure, something called related to the circulation of alpha is of the order of 10⁻². This is like typical value we find without the presence of net flux in this kind of setup, and we're happy. Okay, it's matching with the previous results, but this is not our aim. But I want to just put a caution that, yeah, after that, I'll not talk about circulation of alpha anymore. Forget about this alpha. I'll go for dynamo alpha, which is a separate quantity. You can forget about circulation of alpha, viscosity. Okay. I mean, this is a confusion, but I cannot do anything about because this is the nomenclature people have used over the years.
Historic reasons.
Yes. So forget about it now. Yes. Now, I want to describe something about the mean field dynamo, which is the language I used to describe the magnetic field generation. And I think it's pretty important concept. And I know it's kind of lots of equations. It's difficult to grasp. I took a lot of time to understand this kind of things. But if you, I tried to make it more simple as much as I could, but it's my inability to do it more. I will use equations. Forgive me in that for that, please. So I know it's not a good trend to use equations, at least in US, but I will use it. So you can stop me anytime. So this is the induction equation in the ideal MST limit. Ideal MST means there is no explicit diffusivity. So I think, okay, how can I remove this? And this is basically called heat transfer. Okay,
Yeah,
this term.
We have all seen this.
Okay, okay, good. So yeah, so this is the evolution equation for B. Now what I do, we just decompose the total total magnetic fields and velocity field into a mean part and a fluctuating part, and we plug it back to the induction equation. Then we get something called mean field equation, and this is very similar to induction equation with an additional term which involves E, which is called mean EMF, and which arises because of the correlation between the fluctuating velocity and magnetic field. So this acts like a source term in this equation. Okay, for some terms. Now, if we expand these equations in component forms, you can just write it down and easily find that due to shear means Vy, the velocity in the y direction, will transform the poloidal field. Poloidal field means Vx into the toroidal field. So it will generate toroidal field out of the poloidal field due to shear. So if there is a vertical field like this, the shear will just make toroidal field out of the poloidal field. Okay, clear? This is known as the omega effect. Okay.
Should I be surprised? So this E looks like a second order term.
It is.
What happened in the first order terms? Are these zero?
Because we assume that it's a Reynolds averaging.
So right, we're starting with low magnetic field.
Yeah. Now, if you want to sustain this whole process, you want to get back the poloidal field out of the toroidal field, right? Because there is no external source here. It's only the set field is there. So you want to get back the poloidal field, and there you can get it back something called by alpha effect. And alpha effect is related to E. And how is it related? I will show you in the next slide. But I want to give a physical interpretation of the alpha effect. So, but again, I'm just put a caution here. Don't confuse this alpha with the alpha separation of alpha. Forget about it. So alpha effect is related to helicity. Helicity means twisting motion in the fluid. For example, consider toroidal field, which is rising buoyantly in a stratified medium. Now, if there is some twisting motion in the fluid, it can twist the toroidal field and create the poloidal field lines like this. So you get back the poloidal field out of the toroidal field with an effect of by some alpha effect, and it is related to the helicity. Am I clear? Yes.
Where is the partial B prime partial?
Partial B prime. Sorry,
No, the time derivative of B prime.
Oh, that is another evolution equation that I'm not bothering about. Yeah, that you can also. Yes.
Could you explain again the alpha effect? You said that, let's say you have twisted magnetic field, right?
You have a think about a simple picture. You have a toroidal field in a static
magnetic.
Yeah, like this in a stratified medium, which is buoyant. Now it is rising up. While rising up, there's a twisting motion in the fluid. In the fluid, not in the magnetic field. So it will twist and create loops. Just look at the figure.
So first of all, to put this in context, can you say, so this is like toroidal field, this is Z, this is, in the context of accretion disks, the radial would be out of plane.
No, this is not radial, this is Y.
That's what I'm saying.
Yeah,
right.
so
the radial is out of plane.
Yes.
This is toroidal.
Yes.
Which is Y, and this is vertical.
Yes.
Right?
Yes.
Right.
Yes. So your radial is like this.
Exactly. Yes.
Okay. Yes. Over.
If this is like a stochastic process, what controls the time scales, or is it just a continuous?
So it is a turbulent correlation time. Yeah, tau C. which is right. I mean, you can assume, I assume it to be omega inverse, but it is not always. It's generally less than that.
And why is the rising necessary?
Stratification.
I mean, does it just happen? You can't just have
Are you
this
going
field
to,
line turned in the plane like that. It has to rise up for it to
No,
turn?
it's like a screw motion, right? You need to rise it up.
well, are you going to talk about the Coriolis force and
No,
Parker Dynamo? and
no,
all
no.
this? That's where it
Yeah.
comes from.
Didn't you say there's no shearing in the direction?
No shearing. I mean, that is another thing. We can find it in global simulations, but in shearing balls, yeah.
So there is stratification.
Stratification is there because of the vertical figure. Omega square z. That is the vertical gravity.
But that's key for this.
Yes,
There is, yes, and there is a key that it's turning this way and not the other way.
Yeah.
Right. If you
It's a preferred direction.
I see.
There
This
is a
is so this
preferred
isn't just
sense of
like
rotation.
turbulent motions or something.
Yes.
It has to do with differential
Yeah,
rotation.
this is the.
And
But-
physically it is due to Coriolis force.
By the way, I want to just mention one thing. Generally, large scale dynamo, which is responsible for generating coherent large scale magnetic field, generally found in stratified simulations. But there are one simulation I remember. If you take a very big box, even the non-stratified medium can also generate large scale field, but probably not related to helicity, some other origin that people have not really, I think. So yeah.
And this is happening in a small bubble above the disk, or does it happen in a wide sector?
No, it's fluid. It's like, it's like as Dimitri was saying, Parker instability. It's like flux tubes, like this.
I mean, this, sorry.
Yeah.
Yeah. I mean, this mechanism is believed to be fundamental to all dynamos in the universe, including, the solar dynamo, the galactic dynamo, the
Large scale.
Large scale dynamo. Right, right. That's how the sun operates. So,
Sun is, something. Yeah, like we can.
or at least that's the picture.
Yes. So now, some more mathematics. Okay. So now I'll talk about turbulent dynamo coefficients, which basically characterizes that dynamo. So as I said you earlier, that we are using the language of mean field dynamo. So the crux of the mean field dynamo is that you want to map the mean EMF and mean field through some coefficients. So mean EMF is the E. Let's say it's like chicken and egg problem, but for simplicity, let's say it is the reason and it is the cause and it is the effect. Okay. Because of the presence of mean field, you get the mean EMF, you get the mean field. So cause and effect. That I'm just telling it for brevity. I mean, it's just for simplicity. It is a chicken and egg problem. Like we don't know which is the first. Let's assume it. The idea is that we want to map it and its derivative through some coefficients, alpha ij and eta ij. Epsilon is the Lewis emitters. So, and these are called alpha ij and eta ij turbulent dynamo coefficients. And here I assume that my average is done on xy. So mean quantity is a function of z and t. I averaged over x and y. So there is no dependence on x and y. Del del x and del del y is 0. So there will be only two dependence, del del z and del del t. Then we get this. If I assume other definition of mean field, then this expression will change. Okay. Now, I and j belongs to x and y. So there are 8 coefficients to be determined because these are the quantities we get from the simulations. We need to calculate alpha I and eta. Okay. Alpha yy is basically the alpha effect, which is related to the twisting motion. And etas are diffusivities, which are proposed to be thought to be responsible for the diffusion of the field. And alpha is generation of field. Okay, I know it's getting heavy, but I think it's fine. So how to extract these coefficients? Yes, people have developed different methods. Most popular is test field, proposed by Axel Brandenburg and his collaborators in Nordita. What it does, it basically imposes the test field in the simulation, and it basically takes care of the response from the fluid. But it needs to be run in the simulation time during the runtime, so it's pretty expensive. And also, I guess its reliability in the nonlinear regime is questionable because it's an MRI is a like MRI in the non. We are studying these things in the nonlinear regime. So we took some alternate approach, direct methods. What we do basically fit the EMF to the fields. One of them is SVD, like singular value decomposition. We used it for global simulations, and we can do it in post-process. But it has a problem in extracting the diffusivities because it involves the derivative of the main units, which is problematic. So in this work, we came up with some other method called IROS, which I will talk about.
I'm sorry, so in principle, do these coefficients depend on the fields?
Who knows?
I don't
There
know.
there are properties of turbulence, there are properties
Yeah.
of the velocity field.
Or
But then, of course, non-linearly, the velocity field is affected by magnetic field.
here also I want to mention that it's not only the velocity, but also magnetic field, because MRI is an instability-driven dynamo, so Lorentz force feedback will play an important role.
So there is
So
this
it's like
alpha quenching,
Yeah, all connected.
and it's non-linear, right? Alpha quenches.
And why do you want to find the coefficient? So they
Because
tell
it-
you how much that's the magnetic
Whether
field will
your
grow,
field generation is efficient or not.
and you're
right.
concentrating more on whether it begins to grow. You're like looking at a linear incident.
No,
rate,
we-
or you want to know the final
We are
point.
assuming everything in the nonlinear regime, in the spatial because we have to connect it with observation eventually. Yeah. So this is the method section.
Sorry, okay. So,
Yeah.
If you go back to the previous slide, so you said you want to kind of connect it to observations. Of course, none of these are directly observable.
Yes.
Right.
But
Okay,
efficiency
let's
you can
see.
measure, right? How much field it can generate. Like you can quantify what is the dynamo, how much
Roughly
alpha process
speaking,
is responsible.
So, but okay, so my question is, let's say if you want magnetic field at the end
Mhm.
to predict it somehow, which components of the magnetic field would be of most interest?
If you are looking at the jet properties, probably colloidal field. Because strong colloidal flux is required in order to generate jet in the Blandford-Snack process.
So I mean, the idea is that this framework,
Mhm.
the theoretical framework, will in principle allow you to understand the origin, I don't know, maybe evolution,
Mhm.
is the origin and the level, saturated levels of all three field components.
Yes, yes, that's right.
The
Generally,
X, the Y.
we found around 85% is toroidal, 10% is radial, and 5% is vertical. It is from my global simulations, as well, not
And
from
this,
this.
but this vertical field, which is subdominant, is nevertheless of great interest, right? Like for
No,
jets and
BR is also fine, right? BR is also it's like vertical because we are in spherical polar, not like cylindrical. So yeah. So in global simulation, we generally do it in spherical polar coordinates. So BR is radially outward. So it has also cylindrical as
Okay.
well as BR.
But this is
This is Cartesian. So this is
yeah.
yeah. Anyway, it has another problem. The BZ is 0, net BZ, because it is
because of the assumptions,
yes,
because
yes.
of the boundary conditions.
Yes, that's right. So that's why we don't believe shearing works too much. It's good, but yeah. So I'll just discuss you the key points of the method we did. So we use, and I'm starting from the bottom. We use something called IROS method to extract the dynamo coefficient, which I will discuss in the next slide. And what closure we use. So this is the called closure, the relation between the mean field and mean EMF. So this is the usual closure, which I discussed, right? But we used an ad hoc term, additional term here to capture some time-dependent part of alpha. The reason is that we found that in our simulation, helicity oscillates in time. Okay, so helicity is related to the alpha effect. So it is very natural to think that okay, alpha effect might have some time-dependent part, and to do that, we just make an assumption.
Just to clarify, in sort of plasma physics, especially in known as physical areas of plasma physics like fusion, when one says helicity, one often assumes magnetic helicity, which is
Yeah,
so this is kinetic helicity, right?
it
This
is kinetic
helicity of
as well as
velocity.
current helicity. That I will talk about.
Okay,
I will talk about it both.
but not A dot B.
No, no, no.
Okay.
It's J dot B and so to capture the time dependence of alpha effect, we introduce another set of terms in the equation. Okay, and this is called alpha 1. So when I say alpha 0, it is time independent part, which is the usual one, and a new term alpha 1, which is related to the time independent one. And also we found that basically a small scale dynamo corrects the extraction method. So we remove the contribution from the small scale dynamo in the dynamo field generation by using a low pass filter on the mean EMF and pin fields. Basically make it more smooth. That's all.
And what is the frequency of this term?
Omega is the dynamo frequency. Okay. So
No, sorry. So what is it? Is it measured?
measured. It's
Simulation?
measured from the simulation. So I'm coming to the research. That's good. It's good. Yeah. You'll remember these things. Yes. So what is the IROS method? So IROS method is called iterative removal of sources. And it is basically, we got the idea from an ex-astronomer actually. Yes. So he's a very senior professor in IUCAA, and we are talking about him that we are finding it probably some issue. Then Kandu was discussing with him what you guys do for removal of clean imaging from the dirty background. So what they told that they clean the strongest image or brightest image first, and then subsequently they go for the lower brightness. That's what we do actually. We first fit the EMF for each coefficient separately. We calculate the minimi chi-square, and for minimi chi-square, we choose the coefficient which has a minimum chi-square. We retain it. We subtract the contribution from the mean EMF, and then again repeat the process and subsequently. So this is the matrix we are solving. Is the EMF which you get from the simulation. A is a matrix constituting like fields and currents, which you again obtain from the simulations, and C is the coefficient which you want to calculate. So I think this graphics will show you how to do that. Suppose this is the background, and we have 4 sources. Brightest one, and the brightness decreases in this order. So in step 1, what I will do, we first remove the contribution from the brightest source. In the step 2, we go for the next one, we cleaned it. Next day, we cleaned it. In the 4th, it's all residual. It's the noise term. And we end up with clean image.
But the sources are the A term?
Yeah. What's
source
the
and
connection
C.
between this cartoon and what you're doing here?
Yeah, so source is like C. So each sources are
Actually, what
coefficients.
is this equation? I'm sorry.
So this is again, this is this equation.
No, I don't understand.
Yeah.
But what's the meaning in terms of what is known, what is unknown, what is
So these are known.
What's
This
the
two
logic?
unknown, and this is unknown.
Okay.
We have to find this C coefficients
Okay.
as a function of Z. At
In
each.
the presence of noise.
Noise will be there.
Why is it not straightforward?
Because there is small scale dynamo which is corrupting the field, and there will be some. See, we are essentially doing fitting, and simulation doesn't know about the fitting. It is a direct numerical simulation. We want to set up some connection. We have some model. We want to fit that model into the data. Right. Yeah.
So is this highly overdetermined?
Yes. That's why initially we were going for SVT, but now we are going for more better, where we can set priors as well here in principle. Yes.
Are there any issues with sensitivity, like there's like a region where it really is something that should be subtracted, but it's not sensitive enough, so it appears like it's not.
So here in each jet is independent. So none of the points in space are connected in this method. But you're right, in time they might be connected. Yes, and here basically is, so this sources represent C, the coefficients. And yeah. Now the usual thing gets, I think, forget about method now. The usual thing. So now if you want to study the dynamo, what do you do? First thing you do is just look at the butterfly diagram. What is butterfly diagram? It's the special plot for main fields. So how to read this plot? So this is the x-axis and this is the y-axis. X-axis is time, y-axis is z. So if you want to look at the variation of mean fields with respect to z, the vertical direction at a particular time, you look like this. And if you want to look at the variation of mean fields in time at a particular z, you look like this. So if you, for example, at z equals to 2, you see that mean fields are oscillating in time. It becomes negative, positive, positive, negative, like this for a certain period. And you can just count it. I think you'll find 9 orbital fields. So this is for toroidal field. It's pretty clean. This is for radial field, which is not so clean. And this is actually a source of problem in fitting everything because it is such a noisy term. That we'll see later also. Now, this is a typical feature of MRI simulations with weak magnetic weak initial state field, zero net flux simulations. What happens if we compare it with the geometrically thick RIA, which I have shown you earlier, the thick simulations where disk height is N2R is of the order of 1. So this is the result from one of my simulations. And you see how it changes. The regularity has gone. It becomes intermittent. And this is a typical feature for a geometrically thick disk of H over R, let's say 0.5. So this is the, you can see the stark difference between a thick disk and a thin disk. Just the regularity is totally gone and it becomes intermittent. Yeah. Now we want to see more into the periodicities of the mean fields and EMF. Because you can see it by eye, but you can do more. You can just look at the FFT to look at the frequencies present in the time series. So we have chosen the height between 2H and 3.5 scale height where cycles are really prominent. And if you look at the FFT, you see that there's a peak around F dynamo, which is the primary frequency, which you can easily see in the butterfly diagram with 9 orbital period. But there's another peak, at least at 3 F dynamo, which is present here. Here, even there might be higher harmonics, but let's not talk about them, right? But most prominent is like F dynamo, 3 F dynamo, in all of them, BX, BY, EX, EY.
How does the dynamo frequency relate to the orbital? Yes.
So it's 1 by T dynamo. And T dynamo is like 9 2 pi by omega.
Ah, okay, over there. Yeah, okay. So 9.
Yeah.
Times the orbital.
Like 66 omega inverse, something like that. Anything?
Did you say those dashed lines are the harmonics?
So dash lines are just for guiding your eye. Where is the dynamo frequency? So this is 1 dynamo, 2 dynamo, 3 dynamo. Okay. Oh, sorry, you can see it here, right? 1 dynamo, 2 dynamo, 3 dynamo. So you can see the peaks are present at 1 and 3, and maybe at higher harmonics, but I'm just neglecting because it can be due to noise as well. Okay. And what is the reason behind it? I will tell you more. There are some more story to tell. Now, helicity. As Dimitri was asking me whether it is what kind of helicity is it, what I'm talking about again and again. First is that fluid velocity, like helicity related to the velocity scale. So this is a dot product of fluctuating velocity and vorticity. So curl of V is basically vorticity. And we just multiply with some time scale, correlation time. And this is the classical helicity people talk about the helicity. But MRI is basically instability driven dynamo. So where Lorentz force feedback plays an important role. And it comes out as a back reaction to the kinetic helicity. And I forget to cite Poke in the 1977 paper. Like came up with some other helicity called current helicity and related alpha is alpha mag, which is basically a dot product of Alban velocity, b by square root of rho, and then again it's curled. So it is related to the fluctuating velocity. It is related to the fluctuating Alban velocity, or Alban speed. Okay. Ideally, if the turbulence is homogeneous and isotropic, then your alpha effect should be summation of alpha kinetic and alpha mag. But MRI turbulence is basically image turbulence. It is neither homogeneous nor isotropic. That's why we are bothered about so much about characterizing the dynamo coefficients. We are using this sophisticated method to calculate the tensorial components of alphas and etas. Otherwise, we would have been happy in just using disclosures. And we have seen that now this is the space-time plot for alpha kinetic and alpha magnetic. Now for alpha kinetic, you see that at the midplane, they are small. As you go up, where stratification becomes more and more important, it becomes a larger value. And it doesn't change sign too much. It's almost constant over something. It just takes one sign in the beginning and it remains there. It doesn't work. But for alpha magnetic, it changes sign over time with the frequency, double the frequency of dynamo period. And why is it? I'll tell in the next slide. But it has the same pattern. In the midplane, both the helicities are small or zero. And as you go up, they are becoming non-vanishing. What does it tell?
Yeah. Okay, taus, both of them have the same coefficient.
I assume.
Taus.
I
That's
assume.
assumed, right?
Yeah, I assume.
And how do you measure it? Or...
So we have some idea from some fitting Oliver Gressel did back in, and he claimed that is of the order of omega inverse. So correlation time, for calculating correlation time, we need to like dump the data so frequently that I have not done. Because essentially we have to
principle,
find.
It could be done. But...
Yes, but it has to be very finely chopped data.
Yeah, okay.
So that we can do the autocorrelation of the fluctuating. But there is another story here. What does it mean? Whether in the midplane they are vanishing small, in the as you go up or down, you have non-vanishing values. It tells about the like different types of dynamos happening there. First of all, in the midplane, the small scale dynamo basically grows the field, and it does by the random stretching of the field by the fluctuating velocity field. It is just twisting and turning the field, and it is making the field. But at larger heights, where stratification becomes important, like helicity becomes important, large scale dynamo dominates. Because large scale dynamo is related to the helicities. If there is no helicity, you cannot find any large scale dynamo. So at larger heights, the bottom line is that in the midplane, small scale dynamo dominates. At farther away from the midplane, large scale dynamo dominates. And it creates the large scale field. And this is the reason you can see here in this butterfly diagram, fields are more of like coherent at larger scale heights compared to at the midplane. Because large scale dynamo will generate large scale fields, more coherent fields. Small scale dynamo basically generates the seed fields for the large scale dynamo. Now, again, same thing what we did for mean fields and EMF, we did it for helicity. For kinetic helicity, I don't think there is any peak. We don't think there is anything something like that. But for alpha mag, we found a peak at 2F dynamo, which we can easily see in their butterfly diagram, as well as at 2 and 4. So can you guess any relationship between them? F, 3F, 2, 4, anything? Even number, odd number, more bits, something called bits.
Something called what?
Bits, like bits in the interference of waves.
Oh, okay.
Okay, let's clear it more. So this is related to the helicity evolution equation. Now, helicity evolution equation depends on E dot B. Now, you remember E is basically expansion with alphas and etas. Now, we assume that alpha YY is the dominant term in the expression of E. Let's say E is alpha YY BY. Then this term turn out to be alpha YY BY square, right? Mm-hmm. Now, if BY is a sine wave, let's say, then alpha mag should be sine square. That is 1 plus cos 2 omega t. So it is like 2 omega or 2f, let's say. Same thing. So alpha omega is 2f. To explain us. Next thing, now they are interrelated because E and B is generated by the helicity. So they are related to alpha omega and B. It's like you are interfering two waves. Now it gives rise to it's like 2 and 1, 2 and 1. If you just do sum of these two waves, you get 3, and it's so on. So 3 gives you 4. So if it's a really like a, I mean, I would not be bothered if we can do a more smoother simulations. Probably you get higher frequencies. I'm not sure. We might get, I don't know. But at least it can explain what is going on. Yeah. So this argument is clear. The referee has a question. We got the referee report, by the way, and referee couldn't understand this argument, so I'm trying to make it more lucid. So
just in case the referee is in this.
No, I know the referee is not in this audience. So,
yeah.
This argument is clear.
And just to
yeah.
So this is the time dependent part of alpha.
Yes.
And alpha YY that you said is dominant, right?
Yes.
In this, the way you're estimating this, that is held constant because that's the constant part of alpha.
Yeah, yeah. So that we also found in our analysis, which I'll show, that time dependent, independent alpha is more dominant over time dependent alpha. That's why you can assume that. Otherwise,
yes, right. Otherwise,
yes.
And you will tell us how much more dominant it is.
Yeah. So okay. This is the figure.
All right.
Yeah. So this is the alpha coefficients we measure. Time independent is 0, which is the black line, and time dependent ones are green lines. And this is alpha XX, alpha XY, alpha YX, alpha YY. Don't bother about others. Let's concentrate on alpha YY because this is the alpha effect we expect. So you can see the variation
as a function of height.
As a function of height. Yeah. Z. And we assume that they are a function of Z only. So it's like doing this. So they're negative in the northern hemisphere and tend to be positive at higher heights, but not fully successful. But maybe positive if I extend it further. And it's like there's asymmetry about the midplane. So this is the midplane. Right? For all, I mean, all the coefficients show some kind of asymmetry about the midplane. And you can also see that time dependent coefficients are insignificant compared to the time independent part. And remember that if you want to get the time dependent picture, you have to multiply with the cos 2 omega t. So that's how you incorporate, or we incorporated the time dependence of this alpha coefficients. So even there we are smaller than that at some time. This cos.
It also looks like alpha YY is dwarfed by all the other.
These are more dominant, you mean to say?
Yeah. Alpha YY is the largest
Contributor. But you cannot really tell it from there. We need to look at the magnetic energy equation that we would show that how dominant.
Actually, you're right. Greg is right.
I'm just thinking of the scale.
Greg is right. Yes, because they're all of them are divided by 10 minus.
Yeah, but this coefficient in their absolute values doesn't tell anything.
Okay.
It has to be like you have to look at the contribution in the magnetic energy evolution equation. Okay. That I will show that this is the more dominant over the other terms.
But this also suggests, right? As you have convinced us now that they, as you said, time dependent are insignificant. So why bother about them? Why not just throw them away from the start?
Now we'll throw. But someone has to find it out, right?
Okay. So that's you. So this is the demonstration of this is a non-trivial result.
Yes, yes.
So kind of
we don't have to bother. We don't have to bother about it. Yes.
Oh, okay. So in principle, you could have skipped them from the beginning.
Yes. Now in future we might not use it.
Right. But now you can justify this.
Yes.
Okay.
Yes.
Okay.
Because if you look at like chronologically, you get a time dependent helicity, so you should expect that there should be time dependent alpha, right? Because alphas are directly connected to the helicity. Yeah. Now I'm saying, okay, we don't bother about it because it doesn't have any effect on that. Here. We also compare it to the global simulations where we perform the same experiment, but more rigorously. We don't bother about the black shades because here is the region. So this is from the RIAF simulations. So you are looking at the R theta plane, superloidal plane, black hole is sitting here. This is the region where small scale dynamo dominates. And because it's geometrically thick within H over R1. And none of our analysis is valid here. So this is valid only in the coronary, like at our higher scale heights. And you see that it is negative, and then it tends to be positive in the northern hemisphere. Same trend like here, negative and tends to be positive. So it's very highly likely that the underlying dynamo action is probably similar in geometrically thick disk and thin disk, provided it is MRI active. Like it is the dynamics is dominated by the MRI, not by the others, not like large scale field. Next thing is something called turbulent pumping. It's related to the off-diagonal terms of alpha tensor, and it acts like a turbulent diamond disk. So it is the effect responsible for transport of large-scale magnetic field from turbulent region to the laminar region. So if you have a large-scale magnetic field in a box, and some region you have a gradient of level of turbulence along that box, so it will transport the large-scale magnetic field from turbulent region to the laminar region. So that's why it's called turbulent dimagnetism. So it transports field along with the wind in the accretion disk. And we just plot it as a function of Z. So blue line is like for winds, and black dash is for gamma Z. So here gamma Z is positive. That means it is lifting the magnetic fields from disk to corona. Same thing is doing it in the bottom half plane from disk to corona. Because corona is here, disk is here. Disk is like this, corona is here, corona is here. You can just visualize the picture of a disk. Mid plane is like this, up and top at the top and the bottom is covered. So, and also it shows that it is like turbulent pumping is more dominant at smaller scale height compared to wind. However, at some after some distance, the effect of wind takes over. Yep. Now, so far I was talking about the generation of field, but what is diffusing the field? Because you need to diffuse the field, otherwise it will just draw. So we looked at the diffusivities, and this is the diagonal components of etas, and this is the off diagonal component of etas as a function of z. And you see that eta xx and eta yy are quite different. So that means it is showing anisotropy. So magnetic fields are diffused differently in different directions, which makes sense because, as I told, MRI turbulence is anisotropic. And this is the off diagonal terms, eta xy and eta yx. With eta yx, if it is less than 0, sometimes it can generate in principle colloidal field without having any alpha effect. And people called it shear current effect. And some people have found, like for example, she in the 2016 paper with some assumption.
Not our she.
No, it's not. It's principle.
Yuan, right? Yeah, we have a new faculty member in CIPS in plasma physics just joined this year. Yuan Shi.
No, that's not
the
she.
same.
Yeah, I think she worked with Gemstone.
Okay.
Yeah. So, but they have assumed that some constraint on the coefficients, and then the one. But if we don't use any constraint, we couldn't find anything. Eta yx is always 0. So our conclusion is that probably only the alpha effect is responsible for generation of colloidal field, not any shear current. Now, as Greg was asking, alpha yy is less, like smaller values than the other coefficients, but how you're saying that is the dominant term? For that, we have to look at the energy equation. So we calculate the del bx square and del dt of the bx square terms, and we solve each term in this coefficient, and these are the generated terms. We generate the bx colloidal field. This is related to the alpha yy, and this is related to the alpha yx. So you can see in most of the regions, so red means it is generating the field, blue means it is destroying the field. So alpha yy is almost generating over distance, right? And here alpha yx is related to the turbulent pumping. That means it is transporting field from disk to corona, and probably some of the amounts are deposited here. But, and this is related to by the alpha effect. Same thing we did for dy square. This is shear. As I was talking about omega effect, like from colloidal field, shear can generate toroidal field. So it is the dominant term here. Alpha xx, which is an effect which can create toroidal field out of the toroidal field by some twisting also is there, but it is subdominant. So the crux of this plots is that we generate toroidal field out of the alpha effect, toroidal field due to the omega effect. So it is basically something called alpha omega dynamo. So we characterize it. This is one way of looking at it. No. Last slide. So yeah, I know it is difficult to go through these equations again, but let's see it again. So this is the helicity evolution equation I was talking about to explain those different frequencies present. HB is the magnetic helicity, A dot B, small scale. It is related to the E dot B, eta 0, current helicity. Current helicity is related to the alpha mag, and some flux terms. Now, if you assume that if they are in the steady state, this goes to 0, and let's not assume this. This is to be 0 for the time being. Eta 0 is microscopic viscosity, and this is responsible for alpha yy. Now, one can easily see like if eta 0 is small, C helicity is like finite, then this goes to 0. So it is something called catastrophic quenching. But you can like relieve this process by having some flux here, especially generative helicity flux. It will have some contribution and it will be like that. We want to see this, whether this argument is correct in our simulation or not. It can tell us what is the origin of alpha effect in general. Like helicity is one of the cases, that is true, but how helicity is related to this. So what I did, we took this idea from Vishniak's one of the paper, and which was like explicitly calculated by Gopal and Subramaniam in recent paper, and we calculate the alpha 00 alpha y by from this helicity flux algorithm with these equations. We compare this alpha 0 y like from the helicity equation to the calculated ones from the IROS. So black one is the calculated directly, and this is the estimate from helicity flux, the blue one. Yes, we don't expect to match them like exactly, because it's an because there will be other fluxes like advective flux and other stuff. But trend wise, they're pretty similar. It can explain the negative sign in the northern hemisphere and positive sign in the southern hemisphere. Because in, for example, in Brandenburg, they also try to explain this with buoyancy-driven alpha, but which has some I think disagreement with some of the recent results. But I think we feel that it is an encouraging evidence that it can make it more reliable, this kind of argument. Yeah, so this is the summary slide. We found we have studied MRI-driven dynamo in a stratified shearing box simulations. We found diverse periodicities in mean fields and EMFs. Other than primary frequency, we have seen the presence of higher order terms, which has gone somehow unnoticed in previous simulations. I don't know why. And we use a modified AROS method to calculate the dynamo coefficients, which is more flexible. You can use priors to do that. We found that type of dynamo is going on, it's like alpha omega type. And we found that possible origin of alpha effect could be generative helicity flux, which is like brand new this field. Yeah, that's it. I'm done.
Thank you very much. Are there questions?